Hi everyone. So we have Professor Harish Guruprasad with us. It's a nice opportunity for you to interact with Sir. Sir has covered weeks 1 to 10, 11, and 12 of ML Foundations course, which cover basics of ML, calculus, and probability parts. So please feel free to ask your doubts. You can raise your hands, and one by one you can go on. Harish sir, thank you for taking time out. Over to you, sir.
Hello and good morning, everyone. So you all finished week 12, is that correct?
Week 12 is going on, sir.
Week 12 is going on. Okay. All right. So yeah. So this session is primarily for doubts that you might have in either the initial part, which is something which you would have written tests on already. This is the first week 1 and 2, or the later part, which is the probability part, weeks 10, 11, and 12. So week 1 was simply general funda. I don't think they would have any doubts on that. Week 2 is basic calculus. I hope you don't have any doubts on that as well. But if you have any doubts on week 1 and 2, I think that might be, you can start with that maybe. I'm guessing that will not take too much time. Do you have any questions on the content that I talked about in week 1 or 2? So I'm guessing week 1 and 2 are pretty clear. So I hope there are no doubts there. So in that case, we can move to the probability part, which also most of the content there, both especially weeks 10 and 11, is something which you would have already seen in either stats for data science 1 or 2. So there is a lot of overlap there also, but I thought it was worthwhile to go over it again and emphasize how important this stuff is for doing machine learning. So any doubts in week 10, 11, or 12? Week 12 is just going on, I'm guessing. So week 12 videos, are they out?
Yes, sir. Videos are out.
Okay, great. So in that case, any questions on week 10 or 11? Week 12, maybe I'm guessing a lot of you might not have seen the videos yet. We'll come to that later. Any questions on week 10 or week 11 videos?
Hi everyone. You keep asking your doubts in this course, and it seems you have quite some number of doubts. So it's a good opportunity to have first-hand doubt clearing with Professor. So please feel free to ask your doubts in all these weeks. I hope you all have gone through the probability weeks, the weeks which are going on. So if there is no doubts, looks like you all are pretty clear with all the stuff. So this session is mainly for doubt clearing. So you should make good use of this session by asking your doubts.
Ma'am, the doubts that predominantly are from week 12, actually. 11 and 12 were kind of a repeat of stats 2.
Okay,
so,
great.
Yeah.
Yeah, sure. Yeah, there are no doubts on week 10 and 11. We can move to week 12. So week 12 is something which we just would have started. But by all means, go ahead and ask any questions that you might have.
Sir, week 12, I mean, the number of lectures that I've gone are not too many, but as many I've gone, it seems to be a combination of linear algebra and the stats mixed up together.
Yes.
So I mean, starting from the lecture 1 itself, I kind of have a little bit of understanding problem. I mean, I'm not very clear with the entire video as such.
Okay.
So if you can just walk through like how, I mean, even the bivariate, multivariate normal, when you say Z1 is normal 0, 1 up to Zn, Zd. So what does that exactly mean? Are Z1 vectors which are normal? I mean, I couldn't actually I couldn't come to know what exactly that means.
Right. Maybe first let me share the screen for week 12. So can you see the notes that I have put up there? Is that
yes.
All right. Right. So you by now I'm guessing that you all are comfortable with univariate normal, right? So one-dimensional normal. You are comfortable with that, right? So now you can easily this entire bivariate, multivariate normal is extension. Okay, instead of a single scalar random variable, what if you have a vector random variable, right? So then what does it mean, right? So now we have seen multiple random variables, but that means that if you have a vector random variable, what you need is a joint distribution. You can't, if you have, let's say, height and weight, you can say the average of height is 150. Let's say height is a normal variable with mean 160 centimeters and standard deviation 20 centimeters. And weight is a normal random variable with, let's say, weight as 70 kilograms and standard deviation as 5 kilograms. Something like that, you can have this. But this alone does not give you complete information about the vector height comma weight. That's because height and weight are correlated, right? So it is extremely unlikely for someone to have a weight of, let's say, 80 kilograms and a height of 150 centimeters. That's unlikely. It is possible, it can happen, but it's unlikely. So just by having the densities or the distributions of the two random variables is not sufficient anymore. So once you have a vector random variable, what you need is a joint distribution. Right. So how do you extend the idea of joint distribution to the normal, that is the Gaussian idea? How do you extend that to joint distributions? How to do that to vectors? And that is the crux of this particular topic, right? So how do you generalize this idea, and is that a meaningful idea? And the standard way to do that is to do via linear transformations, right? That is, you have independent normal vectors. Let's say Z1 to ZD are independent normal vectors. And you can imagine that you can put that all together, right? So what's the advantage of independent, what's not the advantage, what's the easy thing with independent random variables? That is, if you know the marginals, you know also the joint, right? That's what this statement is saying here, right? So in general, that's not true. In general, if you know the distributions of height and weight, you don't know the joint distribution of height comma weight. That's not true in general. But if someone also tells you these are independent, then you also know the joint distribution. Why is that? Because you can just multiply that. Right? So that's the joint distribution of a normal vector where everything is independent and standard. For example, for now, it's, let's say, it's standard. Right? So that's the simplest way you can have a normal vector. But that's not particularly satisfactory, because the reason why you even have vectors is that you want to analyze, let's say, height and weight together, right? So not just do height analysis separately, weight analysis separately. So this is not, this is okay. This is still useful, but it is, the idea of multivariate normal is that can we make that idea also clear? That is, the dependence, even if you have dependent random variables, can you model it better than this? That's the question. And the standard way to view this is essentially there is some hidden unknown independent random vector, and then the vector that you are seeing is really just some linear transformation of that, right? So that's the idea. So we'll come to that step by step, right? So that's the reason why you have Z1 and Z2 are independent standard normal random variables. And what you are really seeing, however, that is Z1 and Z2 are there, but that's something which you can't see. For example, Z1 can be something like, let's say, their I don't know what, let's say height and weight are both decided by let's say two independent variables, like, let's say, nutrition and genetics, right? So your diet and genetics decide your height and weight, right? It's not clear how do you express height and weight are scalar random variables, but nutrition and genetics are not really scalar random variables. But you can imagine nutrition and genetics somehow are independent random variables that determine your height and weight, but you can't measure nutrition or you can't measure genetics, right? But you can imagine it is that, right? So you don't really have to know what they are. You can just imagine it is there, and your height and weight are simply manifestations of these independent random variables. So that's the idea here. For example, you can have x1 is exactly equal to z1, but x2 is rho times z1 plus square root of 1 minus rho squared times z2. So immediately you should ask, okay, I can understand that you want to bring in linear transformations. So that is, you have two independent things, and somehow these two are combining together to give me dependent things now. But why am I choosing x1 equal to z1, and why am I choosing x2 is equal to rho times? So in other words, I'm choosing x to be equal to this matrix times z. Right? So this is a 2 cross 2 matrix. Is this clear? That's what I'm doing here. What am I doing here? Is that clear to everyone?
Yes, sir, it is clear.
So what I'm doing here is clear, but the question remains, why am I doing this, right? So linear transformation is fine, all that is fine, but why these particular coefficients? The answer is there's nothing special. It just makes our math easy. For now, just take these two as one example matrix. There is nothing special about this matrix. It's just that it makes the math easier for us to see, right? The reason is that the coefficients squared, the L2 norm of both of these rows are equal to 1, right? So 1 squared plus 0 squared is equal to 1. Rho squared plus square root of 1 minus rho squared is equal to 1. Because that happens to be important for simple mathematics, right? So you can have anything. You could have had A, B, C, D, right? Instead of 1, 0, rho square root of 1 minus rho squared, you could have had A, B, C, D. That would still be a multivariate normal, but that would make the math a little bit more complicated. So to make the math simple, we are using this particular set, right? So for now, let's just take this, right? So now you have X, which is a linear transformation of a standard normal random vector, right? The moment you do this, now X is no longer independent, right? For example, you can take, rho to be equal to 1. If rho was actually equal to 1, x1 equal to z1 and x2 is also equal to z1. So clearly you don't have an independent, the coordinates are not independent. So any row which is not 0 will result in x1 and x2 being dependent now. So now just the marginal distribution of x1 and x2 alone is not sufficient to completely explain x1 comma x2. So that's what this particular thing is doing, right? So now can we get the joint distribution of x1 comma x2 from this, right? So now we had z, which was a standard normal random vector, and I did a linear transformation, and now I have this vector. Now that's the statement, that's the definition itself of multivariate normal. So now I'm going to call this X as as an example of a bivariate normal. I just want to understand what is the joint density of this new random vector. To get the joint density, it's no longer sufficient to just multiply the marginals. It's not, because X is no longer, X1 and X2 are no longer independent, right? So this entire thing just tries to do that, right? So it tries to get the joint density of X. Is that clear?
Yes, sir. But just wanted to understand, sir, when do we use this kind of linear transform, in the sense that we have two vectors, and then, when exactly in application-oriented thing are we using this?
You don't need to use this directly, right? So that's the thing, right? So you don't have to believe that there is nutrition and, I just told you two numbers, like nutrition and genetics, but no one measures nutrition and genetics, right? Height and weight everyone measures, but no one measures nutrition and genetics anyway. The idea is that this is how the world works. That's how we are imagining it. And we are just trying to have a way to model these kind of random variables, where the random variable is a linear transformation of a standard normal vector, right? So we want to model these kind of variables directly, right? Because no one is going to measure nutrition and the genetics. So height and weight is what we are going to measure. So we need to be able to model vectors which are not independent, but you still want some of the properties of Gaussianity, right? So which is normalness. And that is true in general, because a lot of real world random variables are really just linear transformations of some other random variable which is hidden. And it is fairly safe to assume that those hidden random variables are Gaussian. And what you are observing is simply a linear transformation of some hidden. We don't even need to assign meanings to the coordinates of this hidden random variable, right? So I gave it nutrition and genetics. I'm sure someone can come up with two other random variables which could also explain height and weight, right? So the naming itself was arbitrary, so I could have named it anything. The thing is, Z is not visible to you ever, right? So Z is an imaginary object, right? The goal is really to be able to model random variables which are linear transformations of standard normal vectors. That's it. And now once you have, for example, after all this, I've gotten this. Fx of x is basically, let's go to this part, right? So let's say I have written fx of x as this. Oh, that's all I need to know, right? So fx of x, the joint density of the random by two-dimensional vector x is given by this, and it is parameterized by rho, right? Of course, I can also have means. Right now it's a mean zero vector. So this rho expresses something, right? So what does this rho express, this row expresses the degree of correlation between x1 and x2. Right? Why do I say that? That's where you can come back to this expression again. If rho was equal to 1, x2 and x1 are very strongly correlated, right? Because x2 is actually equal to x1. Right? X2 is equal to z1, x1 equal to z1, but that's z1 is something which you never observe anyway, so it's a useless statement. What is more important is that x2 becomes equal to x1 if rho equal to 1. If rho equal to 0, x2 and x1 are completely independent. If rho is equal to -1, x2 is just the opposite of x1. Right? x2 is equal to minus x1. So this rho expresses the degree of correlation between two random variables x, height and weight. Right? Let's say you have normalized your height and weight so that it's mean 0. Now you would reasonably expect that if you height and weight are jointly distributed Gaussians with rho, which is some positive number. Because why is that? Because you believe height and weight are positively correlated. Right? And if you really measured height and weight and you tried to fit a Gaussian to this, you will find that the rho for the joint data of height and weight will be positive. It will not be 1. Height is not exactly equal to weight. So height, we don't mean that height is exactly equal to weight. We just say that height is just a linear function of weight. So if it so happens that height and weight in kilograms is exactly always equal to height in centimeters divided by 2. Right? This is not going to be true, obviously, always. But if that were really the case, then rho would be exactly equal to 1. Because once you know height, you know exactly what weight is. Right? Once you know weight, you know exactly what height is. So rho would be 1 then. But that's all hypothetical. What you really have in the real world is just measurements of height and weight. And you want to be able to model this, model these kind of vectors in the real world realistically, right? So if you modeled height and weight as independent random variables, you would have kind of missed out an aspect of it, right? If you just said height was and weight are independent random variables, you could do that, right? I mean, no one is going to put you in jail for doing that, but you have missed out an aspect of height and weight because they are correlated. So to express that also, you will need rho. Yeah, does that help?
Yes, sir, it does. Thank you.
And as I told you, there's nothing special about that particular matrix. There is nothing special about 2, right? So we have used 2 random variables here. You could have easily extended this to multiple random variables and other matrices. That's what this particular thing is doing, right? You could have had a general multivariate normal, which is that your random vector x is simply some linear transform of the standard normal vector z, a times z plus some mu. Mu is some mean vector, right? And now you can write down the joint density of this random vector. And if you do that, you get back this particular expression. This expression you might have seen in school or somewhere else also, which is the multivariate normal vector. You might have seen this as the definition of the multivariate normal vector, right? So you might have seen that if the definition of a multivariate normal is that the density of a multivariate normal is given by this expression. You might have seen this expression given directly to you. That is also fine, right? I mean, you can just take that as granted and see that, okay, the definition of a multivariate normal vector is this, and I'm going to go ahead with it. You can always do that. But what this particular analysis gives you is that why this particular formation of sigma inverse 1 by 2 power d by 2 square root of determinant of sigma y, this looks complicated. You understand standard normal. Standard normal is nice. You have 1 by root 2 pi e power minus z squared by 2, which is pretty, it's good looking, right? But the moment I have this, now this looks complicated. It's not clear what are the moving parts here. So once you look at this, now once you have done this analysis, you can understand, okay, what's happening here. The parameters of this distribution are mu and sigma. Right? Mu is the mean vector and sigma is the covariance matrix. Okay? And you can completely ignore, once you have data of x, all this is just trying to explain what's happening. You can completely ignore that and you can just directly estimate your mean and covariance and be done with it. Right? So because mean and covariance completely explain the density of x. This z and all that is to motivate this expression, right? I mean, for example, if you believe in this expression already, then you can kind of ignore a lot of what's happening here and go ahead and say, okay, this is multivariate normal. I believe in the religion of multivariate normal, and this is the expression for it, right? No questions asked. If you believe that, then you don't really need all of this stuff. You can just take, this is the expression of the multivariate normal and be done with it. But sometimes you might want something more than that. You might want to say, okay, why this particular expression comes into play. You might want to understand the multivariate normal. You might want to generalize the idea of multivariate normal to, let's say, a multivariate Laplacian or multivariate something else, exponential or something like that. Then how would you generalize these kind of ideas? To do that, you need to understand where the multivariate normal comes from. And that was the goal of this particular module. Yeah.
Yes, sir. Thank you, sir. This makes it quite clear.
Okay, great.
Yeah, thank you. Sir, I had another question, but it's quite a little bit ahead, actually. We find out the maximum likelihood. We used to do that in stats 2 as part of stats 2, but in that we weren't doing the negative, like here you named a thing called risk of theta, and then you took the negative log.
Yes.
So why is that? Because until stats 2, we were only doing the log, we were differentiating it, equating it to 0, and we got the maximum likelihood.
Mm-hmm.
So why do we do this negative log here?
It's the same thing, right? So if you can either maximize the log likelihood or minimize the negative log likelihood, it makes no difference. It's the same thing. This is so that you get more comfortable with the idea in machine learning. In machine learning, almost always you will minimize risk functions, right? So minimize, that's a standard paradigm, right? I mean, you can minimize log of the minimize the negative log likelihood, or maximizing the log likelihood is exactly the same thing. Right?
Okay.
But just that in convention, you end up always minimizing a risk function. So, for example, in maximum likelihood, the risk function is simply the negative log likelihood. You could have, instead of minimizing R of theta, you could have just maximized minus R of theta. It makes no difference, right? So the argmax, the minimum value will be different, but the max minimizer or the maximizer will be the same.
Okay, sir.
And setting the gradient to 0 is really just a tool, right? So what you really want is maximize the log likelihood or minimize the negative log likelihood. And setting the gradient to 0 and equating it and doing that is simply, if you have done the optimization module, you know that that does not guarantee that you are the minimizer or the maximizer, right? So that's only a first order necessary condition. So in some situations that is sufficient. But in some situations it's not. So you should always be careful when you are just setting gradient to 0, you are not doing something else, right? So setting gradient to 0 simply means that it's a critical point. It could be either a minima or a maxima or a saddle point or anything like that. Right? So that's also something which you should be aware of. But in a lot of, for example, let's say Gaussian normal mean or things like that, R of theta has this kind of structure. And this kind of functions are called convex functions. And for convex functions, setting gradient to 0 is exactly the same as finding the minimizer. That's something which you should be, you should try to make a distinction between finding the minimizer of negative log likelihood and setting the gradient to 0. Setting the gradient to 0 is an algorithmic way to get at the minimizer, but it's not always guaranteed to work. Right? So that's something which you should keep in mind.
Yes, sir. Thank you.
Right. Yeah. Any other questions in week 12?
May I ask the doubt in week 11?
Yeah, sure. Go ahead.
So, sir, in lecture 6, you have explained the transform random variables. So, I'm just not sure about, like, can you just briefly explain that? Basically, how that you have explained that some values are belonging to the rectangular, like the corners of the rectangles, and then it transformed into the parallelogram and all those things. I'm not getting, like, how those rectangle and parallelograms have come into the picture.
All right, let me just open. Yeah. Can you see the week 11 content?
Yes, sir. Yeah.
Transform that. Okay. Okay. So here's the idea, right? So that is, you have, what's the goal here with transform random variables, right? So that is, you have two random variables, W and X, whose joint density you know, right? That's the setting here. You have two random variables, W and X, whose joint density you know. They could be independent, they could not be independent, doesn't matter. The point is, you know their joint density. And now you define, now you see two other random variables, Y and Z, which are functions of W and X, right? Y is G of WX, Z is H of WX. And for the sake of simplicity in this particular section, we'll assume that they are actually invertible functions. What do I mean by that? I mean that not only Y, Y is a function of G, W and X. W and X are also a function of Y and Z. So by that, I mean that if you, from W comma X, you can get Y and Z. From Y and Z, you can go back to WX. Right? So it's, for example, X squared is not an invertible function because -2 and +2 both map to 4. Right? So if I say what is the inverse of 4, you don't know the answer. It is either -2 or +2. But something like Y equal to 25x is actually an invertible function. Why is that? Because from X you can get Y, and from Y you can get back to X just by dividing by 25. So that's the invertible transform idea. Is that clear?
Yes, sir. That setting is true.
Yeah. So the goal is, now you have the joint density of W comma X, and you want the joint density of Y comma Z. Right? That's the thing, right? So now you know the transforms GH and QR, and you want the joint density of Y comma Z from the joint density of W comma Z X. That's the question. So let's go at it from first principles, right? So what is the joint density of Y comma Z? Let's say Fyz of Y comma Z times dy dz is simply the probability of the random variable Y comma Z being in this particular square or rectangle. Is that clear?
So that rectangular, like I'm not getting like how you have created this rectangular, maybe the square.
Right. So now let's go to the definition of density itself, right? So what's the definition of density? Let's go to. Right. So you know this for individual random variables. We can also do that for, right. This is for individual random variables. Multiple random variables. Yes. So this is the definition of density. Is that clear? Is this, and you know this definition, right? So
Yeah.
Fy of X comma Y is the probability that X belongs to the line segment X to X plus dx, Y belongs to the line segment Y to Y plus dy. Right? So if X belongs to the line segment X, saying that X belongs to, let's say, for example, if I say that you can imagine two axes X and Y. When I say X is in the range of X to X plus dx, Y is in the range of Y to Y plus dy, the joint, not the joint, the coordinate X comma Y is in the rectangle given by 4 points, which is X comma Y, X plus dx comma Y, X comma Y plus dy, and X plus dx comma Y plus dy. Is that clear?
Yes, sir. Now clear.
Yeah. So that's the that's because of a definition of joint density. That's where the rectangle comes from. Right. So this is the joint density times dy dz. Or if you are confused with dy dz here, you can bring the dy dz to the denominator here, which is exactly what the joint density of Y and Z is. Right. Is the first expression clear?
Yes, sir.
Right. So I have not written in a semi-symbolic and semi-graphical way of doing this, so which is not fully formal, but I think this does a better job than writing the expression out. Is this so? This is the first expression. Okay, now that's by definition true. But now what can we say about? We need, however, the left-hand side is fine, which is just what we want. We want the left-hand side, but on the right-hand side, we only want the joint density of W and X. We don't want this. Right? So that is where you can use the fact that YZ is invertible, right? So when you say that Y comma Z should belong to this particular rectangle, then what should W comma X belong to? That's the idea, right? So because it's invertible, I can say exactly what it should be. For example, that means that it's the inverse of this particular rectangle. Inverse given by this particular QR function, right? So that means that you can apply the Q function to y comma z and r function to y comma z. So which means that it's going to be some other shape. Ignore the fact that it's a parallelogram for now. You will see it's a parallelogram soon, but at least this left corner, can you see that's simply going to be q of y comma z, comma r of y comma z, right? It is the probability that w comma x belongs to some other set. So the probability of y comma z belonging to this particular set is exactly equal to the probability of w comma x belonging to the inverse of this set, right? The inverse of this set simply means that it is the transform q comma r transform of this set. Right? So I just, for simplicity, you can imagine you are applying the functions q comma r to every point on this, or let's say every vertex of this rectangle, right? So that means that you apply q comma r to the point y comma z, you get q of y comma z and r of y comma z. And similarly, you can apply it to this point here, which is q of y plus dy comma z plus dz, comma r of y plus dy comma z plus dz. And similarly, we will get these two other points also. So now you have 4 points. Now we can ask the question, okay, now I have 4 points, will it still be a rectangle? Right? So any 4 points, if any 4 two-dimensional points, if we put in, it's not a rectangle, right? It's a general quadrilateral. What will it be? What we can show is that it simply follows from basic calculus that it is it no longer needs to be a rectangle, but it will still be a parallelogram. That's what we can just write down the 4 points. That you can do pretty easily, and then you can just argue that the two edges are going to be parallel. They might not no longer be at 90 degrees to each other, but they will still be parallel. Take that for now from me. Right? At least the two ends are going to be pretty clear. This is q of y comma z and r of y comma z. This end is going to be, can you see my mouse cursor?
Yes, sir.
Right. So this end is going to be q of y comma z and r of y comma z, and this end is going to be q of y plus dy comma z plus dz and r of y plus dy comma z plus dz. And these, if you want to know, these points are also, this point is going to be q of y plus dy, sorry, q of y comma z plus dz and r of y comma z plus dz. And this particular point is q of y plus dy comma z and r of y plus dy comma z. Right? So that's the 4 points. And those 4 points will form a parallelogram. How is that true? That comes from the first order approximations of Q and R. I think we've done also that. This is basically uses ideas from the second week of the course, which is simply first order linear approximations. It comes from linear approximation. So what you will end up with is having a parallelogram. All right. So now that still does not solve our question. Now I have just written in some other form. Now I want this answer, right? So here is where you can use the fact that dy and dz are very, very small. Right? If dy and dz are very, very small, then you can assume that within this particular parallelogram, the density of w comma x is constant. Right? So density of w comma x can be a function of w comma x, obviously. But if you make the parallelogram very small, or that is, if you make the rectangle very small, then the parallelogram will automatically become small. Then within that parallelogram, the density of w comma x is constant. Right? If that is the case, then what can you say about this particular thing? Right? Let's say within this parallelogram, the density is constant. Then what is the probability of w comma x belongs to this particular parallelogram? What is that? It's density times the area, right? So now the probability of w comma x belonging to this particular parallelogram is simply equal to the density of any point in this parallelogram. Let's just take the leftmost point because it's easy, which is fwx of q of y comma z comma r of y comma z times the area of this parallelogram. Right? So here is still dy dz if you want. There is one. Can you imagine there's an intermediate step here, which is fyz of y comma z times dy dz is fwx of q of y comma z and r of y comma z times the area of this parallelogram. And the area of this particular parallelogram is given by the determinant of this matrix, which is the Jacobian. Right? So if you are not sure how this comes from simple geometry, right? So how do you compute the area of a parallelogram? Or how, you can just write it down as a matrix, and the determinant essentially corresponds to the area of that parallelogram. This comes from linear algebra. hopefully, I mean, this might be the first time you're seeing it, but in a standard linear algebra course, this would be covered. But this is still a geometric fact. It has nothing to do with probability or anything. It's just a geometric fact that if you want the, so it's a signed area. The area can be signed also. Area can be negative also. That's why I'm saying absolute value. Right? Why is that? Because I could always swap the rows. Then the determinant would change sign, but the area is really meaningless, right? So area can never be negative. So that's why what you get is a signed area. So that's why you take the absolute value. So that's this J, determinant of this J here corresponds to the area of this particular parallelogram. So now we have the left-hand side, right-hand side is all nice. That is, you have Fyz of Yz. Left-hand side is the density of joint density of y, z, which is what you want. And the right-hand side is Fwz, Wx of Q of y, z and R of y, z, which is what you have, right? So the left-hand side is what you want, which is a joint density of y, z. The right-hand side is what you have, which is the joint density of w, x, evaluated at some other point, right? So it's not evaluated at y, z anymore. It's evaluated at Q of y, z and R of y, z. That makes sense. And however, you have this extra term here, which is the Jacobian of this particular matrix. That's the this is exactly what you wanted, right? So left-hand side you wanted the joint density of y, z. Right-hand side you have the joint density of w and x. So what this helps you is that you can get the left-hand side from the right-hand side. So is the goal of the thing and the broad idea clear?
Yes, sir. Now it's clear.
So you can, that's why I give a very simple example here, where W and X are actually independent. So it's easier now. W and X are independent. And actually I make the transform as also, you can clearly see it's an invertible transform. Y is W plus X and Z is W minus X. Right? So clearly this is an invertible transform. Why is that? Because you can get back W and X from Y and Z. Right? So that's what you do here. W is Y plus Z by 2, X is Y minus Z by 2. And J is the Jacobian of the inverse transform Q and R, which means that it's the Jacobian of this particular transform. So that's a pretty easy transform. So it's half and half minus half. Why is that? Because y by 2 plus z by 2, that's half. Y by 2 minus z by 2 is half minus half, right? So this is the Jacobian matrix of this particular transform, inverse transform. And then you can compute the determinant of this, which is going to be half. And then now you can say, what is Fyz of y, z? This is simply Fwx evaluated at the inverse of w, x, which is y plus z by 2, y minus z by 2 times half, right? So that's F. So, and now we can use the fact that w and x were assumed to be independent. So now Fwx of this is simply Fw of this times Fx of this, and then you have the half here. So now you can write down what this is going to be. And so I've given you the answer here. What will the joint density of y, z look like? It will essentially be 0 outside this diamond, and within this diamond it's going to be equal to half. You can clearly see now it's not independent, right? So if it is independent, you will not have something like this, right? So within this diamond, it's going to be non-zero, which is exactly equal to half. Density is going to be half. Outside this diamond, it's going to be 0. For any independent set pair of random variables, the joint distribution will always be something kind of a rectangular shape kind of thing you will see, right? So that's not true here because there's a diamond shape here. And that's kind of obvious because y and z are w plus x and w minus x. So clearly, for example, if I know w plus x is equal to, if I know y is equal to 2, then z has to be equal to 0. Why is that? Because y is equal to 2 means that the only way I can achieve 2 is w is equal to 1 and x equal to 1. Right? So that means that z cannot be anything. Z has to be 0. So y equal to 2 implies that z equal to 0, and so on. Right? For example, if I know, for example, z is equal to, let's say, 1, right? If you know z is equal to 1, then the only way I can get z equal to 1 is if w equal to 1 and x equal to 0, right? Which means that y also has to be equal to 1. That means that knowing y gives you some information on z. So y and z are not independent variables, even though w and x are actually independent. And that is reflected here, the joint density of y, z. So you do have this kind of structure, which means that you cannot factorize this in terms of y and z, right? So Fyz of y, z, you can't write it as some g of y into h of z, right? So you can't do that because this has this structure, and you can also visualize that structure in this kind of figure. So this is a very simple case where everything is linear, but all of this applies even if the transform was not linear. There is a little bit more tricks to go through that because the j is no longer going to be a constant, right? So this Jacobian in this case happened to be a constant, half minus half, so it was nice. But it is possible that J also depends on Y and Z, right? So in that case, you have this, but it's still fine. You can just do that, and you can just substitute the left-hand side values of Y comma Z here, right? So this half here might also be a function of Z, Y and Z. That's still fine because left-hand side you have Y and Z. You can just substitute the values here. If it is linear, if the transform is linear like this, where Y is W plus X and Z is W minus X, then this J is going to be a constant. It does not depend on Y and Z. So that's the easy case. Does that help now?
Yes, sir. Thank you.
Any other questions? Excuse me. There's something in chat. If you have any other questions, please ping now, right? So that because this is the right time to have these discussions. Because a lot of the content is overlapping from stats. Just a couple of extra geometric ideas that you get, for example, in the transform random variables, in, for example, in Gaussian mixture models and so on. So it's just moving a little more advanced than stats for data science.
Does anybody have any questions? But if there are no other questions, I remember from week 1, density estimation is one topic where many students had doubts. If you could briefly touch upon that, sir,
Okay.
before we close the call. Yeah.
Okay, great. So Charles uses a question. So how can you give a use case in ML of how to use these concepts we studied? Okay. So I think, for example, for density estimation, the easiest example is clustering, which we study in week 12. For example, let's go here. Right. I think I shared week 11. No. What's this? I cannot. Yeah. Right. So you might have to do clustering, right? So for example, you might have data like this. So you can imagine two-dimensional data, right? For example, let's say you ask people whether how much they like one movie and how much they like another. Let's say how much they like, let's say, Lord of the Rings and how much they like Spider-Man, right? So you ask these two questions and you put that in a scatter plot, right? So you have, yeah, I don't know if this data makes sense, but that's just an example, right? You have two numbers, which is how much you like movie one, how much you like another movie, and then you ask this question to, let's say, 1,000 people, and then you do that in a scatter plot. And now you want to group people into, let's say, 3 groups. You don't really know, I mean, you have not asked them any other question. You asked just these 2 questions, and you just have this, and you want to group them into 3 meaningful groups. How do you do that? And the standard way to do that is by what's called clustering, right? So you cluster these data points into however many groups you want, and then hopefully the thing is that each group represents a meaningful classification of people. Right? Maybe there are people who like epic fantasy but don't like modern fantasy. There might be people who like Spider-Man just like Spider-Man and don't like all elf languages and so on, right? So you might have different types of people, and each of these group of people have a meaningful thing, right? For example, you might want to decide how to market a new movie that you have. to different people based on this idea. Right? So you might market your new movie as primarily, let's say, we're doing Superman stuff to one group of people, and we might want to market your movie as mostly doing, let's say, elves and orcs to another group of people, and so on. Right? So you might want to market your movie to different people based on this particular grouping. You can't ask this question directly, right? So you can't ask the question and say, would you like to be marketed via Superman type advertisements, or do you like to be marketed by orc and elf kind of advertisements? It's not a meaningful question to ask, but you can ask the question, how much do you like let's say Lord of the Rings, and how much do you like Spider-Man? That's a meaningful question to ask, and you can do that. So this clustering, and now the target becomes clear. That is, you want to group this data points into, let's say, 3 groups. And how would you do that? Right? And the standard way to do that is clustering. And the standard algorithm for doing that is the k-means method, which is essentially an extension of the, not extension, a special case of the expectation maximization algorithm, right? Which is what is done here. So this is an algorithm that is done. Right? So how are these different tools that I talked about used here, right? For example, how is the multivariate Gaussian used here? Because you can clearly see that each of these components are multivariate Gaussians. It's easier to view them as multivariate Gaussians rather than as anything else, right? So you can, and because that's how the data was generated, but it's easy to view, easy to model within each group how much you like, let's say, Spider-Man versus how much you like Lord of the Rings. That happens to be a multivariate, bivariate normal. Let's say that's how the truth is. Then by estimating the mean and covariance of each of these groups, you have something meaningful to use. So this is a pretty vague situation, but this is how most problems in machine learning work, right? So how do you break it down into something which is more mathy, right? So instead of viewing them as, let's say, house prices, you want to predict house prices from house data, you will break this down into easier problems. Instead of trying to say, okay, how do I, what is the right marketing strategy? You want to break it down into easier problems. Like, okay, I want to first group people into some groups and then do different things to different groups. And how do I group them? Well, I ask these kind of questions and then do, let's say, expectation maximization based clustering to get these groups, and then use those groups. That's how you might use these tools in machine learning. I know it's pretty vague, but does that help?
Yeah, thank you.
And Anamika was asking some questions about, said that a lot of you had doubts in week 1, is it?
Yes, sir. Density estimation students were asking a few doubts, I remember, from week 1. So
I'll do that. So what density estimation is, and I've already given you one example of density estimation in terms of Gaussian mixture models, but in general, density estimation is just this, right? So you have data. There's no X and Y. You just have a bunch of vectors, right? And you want, there are several goals here. The one is you want to just understand the data, or you might want to generate similar looking data, right? So that's what I said. Let's say these are tweets, right? So each of these XIs are, let's say, tweets, and you want to generate another tweet which looks similar to these tweets. Of course, you can just copy paste a previous tweet, but then you are going to get found out, right? So if you have 1,000 tweets and someone says, okay, generate 1,001st tweet, you can just go and copy paste the 78th tweet. You could do that, but that's not original, right? So you're not generating anything new. But someone can say, okay, write a robot which generates tweets similar to these. That's a question someone can ask. And density estimation is useful for that, right? So how do you use that? Now you have these 1,000 tweets, say, and with that, you kind of build a model which gives a probability score to all possible tweets. So that's what you are looking for. Now you want to build a probability model, which is that probability of some, if you sum over all possible tweets, which is, let's say you have 128 characters, A to Z power 128, probability of tweet is going to be equal to 1. Why is that? Because I want these to be probability scores. Now, once you have this, and someone says, okay, now you have generated this, now you have this probability function. Can you generate a new tweet? How would you do that? Well, you can just sample from this distribution, right? So, for example, you might have a situation like probability of AAA BBBCC is 0, right? Because it's not a meaningful tweet. But you can say probability of apples are delicious is somewhat non-zero, right? So it's obviously not going to be equal to 1 because that's not the only tweet. But you might have some other non-zero value here, and based on that, you could sample that particular tweet, and then you could generate that tweet. So the real machine learning part comes in finding this function, finding this probability function, so that the probability of a particular tweet is high if it is similar or close to one of these data points, and it should be low if it is far away from all these data points. That's really all you can do, right? So, but what does far and close mean, right? So those are English terms. That's not something which I'm going to go into great detail now, but that's the goal, right? So the goal is to have a probability function which will give high values to tweets which are similar to the tweets that you've already seen, and low value to the tweets that are not similar to the tweets that you have seen. It should be a good similarity function. You can't say that it's exactly the same as the previous tweets, then I'm going to generate it. Otherwise, it's not similar. If you do that, then you will just be repeating the tweets. You don't want that. You want some kind of creativity, let's say, which means that you can't say a tweet is similar if it exactly equal, right? That's not a good similarity metric. The goal is to have a probability function that the probability of X is large if X belongs to this data set and low otherwise. That's the goal here. And what is the loss of any such thing? Well, you can just say, well, the loss is simply you sum over all the tweets or all the data points, the negative log likelihood of P of Xi. So when will this be small? This will be small when log P of Xi is large, or in other words, this will be small. This particular loss will be small when P of Xi is large. Right? So if you have a situation, if you have a probability model which gives large values to all the tweets, all the data points, then you have a good model. That's the idea. Okay, so let's make something more concrete. Let's say you have 4 data points. Let's say x1, x2, x3, x4. Right? So x1 is just a scalar line. It's not a tweet anymore. It's just a real value. So you have 4 numbers. X1 is 1.2, x2 is 1.9, x3 is 4.3, and x4 is 4.8. And the goal is to find a model which gives high values to these things, but low values to things not here. But it's not any possible function, right? So now you only have, let's say, 4 candidate functions. The first candidate is probability it's uniform in the range of 3 to 10. The other is uniform in the range of 0 to 10. Another is uniform in the range of 1 to 5. And another is uniform in the range of 3 to 5. You can have, let's say, these 4 candidates. You can ask the question, out of these 4 probability functions, which is the best? Right? All of these are valid probability functions. Why is that? Because if you integrate it over the range, it's going to be equal to 1. Right? That's why I said uniform. Right? So it's a valid probability function. So what would the scores of the 4 data points be with this probability function? By score, I mean just evaluated, right? So it means that if you evaluate these 4 data points with these probability functions, is going to be 0 and 0, because 1.2 and 1.9 are outside 3, 10. Right? So, and you have 0, 0, and 3 data points 3 and 4 are within the range of 3 to 10. So it's 1 by 7, 1 by 7. Why is it 1 by 7? Because it's uniform in the range of 3 to 10, which means that the density has to be equal to 1 by 7. So what about uniform 0 to 10? Right? If you do that, the 1 by 7, 1 by 7 actually reduces to 1 by 10, 1 by 10. But what it does help is that 0, 0 becomes 1 by 10, 1 by 10. Right? So why is that? That's also obvious, because all these 4 data points are in the range of 0 to 10. So all of them will have probability scores of 1 by 10. Right? Similarly, you can do the same thing for 1 by 5, 1, 5. So 1, 5, you'll see that also covers all the 4 data points, and it's a smaller bit. So you will find that all the values here are actually larger, right? So it's 1 by 4, 1 by 4, 1 by 4, 1 by 4, which is greater than 1 by 10, 1 by 10, 1 by 10, 1 by 10. And now out of these, you can do the same thing for the 4th model also. You'll get 0, 0, half, half. And now we can find the log likelihood of, or the loss of all these 4 models. So what is the loss of this model? What is the loss of the fourth model? That's going to be equal to infinity. Why is that? Because you have minus log of 0 here. Right? Minus log of 0 is going to be infinity. So this is going to be infinity. Similarly, P1 is also going to be infinity because you're going to have minus log of 0. Right? So that means the loss of these models P4 and P1 is actually infinity, which is greater than anything finite. And what is the loss of models P2 and P3? You can compute that. And you will find that the loss of model P2 is larger than loss of model P3. So out of these 4 models, the model that has the least loss is simply P3, which is kind of meaningful, right? So if you look at these 4 models, the model that seems to best explain the data is P3, because P3 is saying the data is uniform in the range of 1 to 5. These other 3 things are saying something which is less intuitive than P3. That's all there is to density estimation. There is nothing. I mean, an algorithm has to come up with these candidates also, right? So no one is going to give you, in the real world, no one is going to give you these 4 options and say choose the best option. People are just going to give you the data and say give me a good model. Right? So that's a harder problem, but that's separate. Right? The idea of density estimation is pretty simple. That is, if someone gives you options, you can choose the best option simply by choosing the model which has the least negative log likelihood. How do you find these options is a different question altogether. That's that's where really machine learning enters the picture, but that's a separate question. The first question is, if someone gives you, let's say, two models, you should be able to say model 1 is better than model 2 because that has a better, smaller negative log likelihood. That's all there is to density estimation, at least in this particular week, right? So later, for example, in week 12, we do density estimation, right? So how do we do that? Well, there we don't give multiple choice options, but rather we say that, okay, I have data. I'm saying that this data comes from a normal with unknown mean and variance, right? I don't know if it is coming from, let's say, variance is also fixed. I don't know. I know that, I mean, I am assuming that, or I'm not even assuming that. I mean, I have data. You're asking, okay, I'm giving you these options, which is option 1 is that it is coming from normal with mean 0. Option 2 is it's coming from normal with mean 0.01 and so on, right? So you can have infinite options where the normal distribution, the means are different. And out of all of these, you want the model or the probability distribution which has the least negative log likelihood. And that's what you are doing when you computed the likelihood and then you maximized that over the parameter mu. You can essentially view maximum likelihood is essentially generalizing this idea where you have infinitely many options instead of just the 4 options here. But at the end, it's still doing the same thing. Right? Any questions on this? And you can generalize. I mean, I've done that here also. That is, you can have, let's say, these data points, and then you want to choose between 2 Gaussian mixture models, which is the one at the top here, P1, or the one at the bottom here. And you can see that the one at the bottom here explains the data much better than the one at the top. And so model P2 is better than model P1. Is that the best model? No, we are not saying that. Right? So we are by no means saying that that's the best model. If someone gives you just 2 models, you can say, well, one model is better than the other. What is the best model is a different question altogether, which is generally not always solvable. Yeah. Any questions on this?
Thank you, sir. I think this would have made things clear for the students. Any questions on this or any other questions, students? There are a good number of participants as we see, so it'd be nice if you ask your doubts. Otherwise, we should close the session.
Yeah, that's fine. So if there are no other questions, we can close now. If there are any other doubts, also you can maybe, if there's a forum and if you put it there, which cannot be answered by the TAs can get to me and I'll try to answer it. So please use the forum also and ask the TAs the questions. And if they cannot answer, they'll get back to me and I'll be able to answer.
Yes, sir, sure. Thank you, sir.
Thank you very much, Anamika. Thank you.
Thank you. Thanks, everyone, for joining in. Please post your doubts in discourse if you have any more. Thanks and bye.
Yeah, thank you all.